The observable universe is 93 billion light years across, not 93 billion light years in some approximate or poetic sense, but as a measured physical diameter, the distance from one edge of the region we can observe to the opposite edge, stated as a number arrived at through careful calculation. That number is worth sitting with for a moment, not because it is large, which it is, and not because it is difficult to imagine, which it also is, but because it contains a quiet puzzle that becomes more interesting the longer it is held. The universe is 13.8 billion years old. Light travels at roughly 300,000 kilometers per second, which is as fast as anything in the known physical world is permitted to move. And yet the observable universe is not 13.8 billion light years in radius. It is nearly 46.5 billion light years in radius. Light has not had time to cross it. The universe is wider than light can account for. The reason is that space itself has been expanding, not that matter has been flying outward through some pre-existing room, but that the room, the fabric of space, has been stretching in every direction since the first moments after the Big Bang, and it continues to stretch now, at this moment, while everything in the universe goes about its ordinary existence. Distant galaxies are not moving away from the Milky Way in the way that a car moves away from a building. The space between the Milky Way and those distant galaxies is simply growing, increasing the distance between them without either one going anywhere in particular. This means that light emitted by galaxies at the far edge of the observable universe was not emitted 46.5 billion light years away. It was emitted much closer, from a position that has since been carried far out by expansion, the way a message in a bottle might be carried far from where it was dropped by a current that did not exist when the bottle first entered the water. 93 billion light years, then, is the diameter of the region from which light has had enough time, accounting for this expansion, to reach us. Beyond that boundary, there is almost certainly more universe, continuing in some unknown quantity that observation cannot yet determine, and may never be able to determine, since the expansion of space carries the most distant regions away faster than new light can arrive from them. The edge of the observable universe is not a wall, it is a horizon, the furthest distance from which light has had time to arrive, with everything beyond it present and real and simply not yet visible. That space is expanding raises a second question, which is what, precisely, is expanding into what? The answer, as far as current physics can establish, is that this question may not have a meaningful form. Space does not expand into something else. It is not inflating like a balloon inside a larger room. The expansion is a property of space itself, and to ask what lies outside it is to ask what lies north of the North Pole. The question is grammatically complete, but physically empty. The universe does not have an outside into which it grows. It simply grows. Within this expanding volume, the distribution of everything that exists is uneven in ways that matter. Ordinary matter, the kind made of protons, neutrons, and electrons, the kind that forms stars and planets, and every living thing, and every instrument ever built, accounts for approximately 5% of the universe's total energy content. The remaining 95% divides between dark matter, which pulls gravitationally without interacting with light, and dark energy, which is associated with the expansion of space itself, and which fills the increasing volume of the universe as it grows. Both of those categories are observed through their effects on ordinary matter and on the behavior of light. Neither has been directly detected in the sense of a particle captured or a field directly measured. They are real in the sense that the effects attributed to them are measured and documented. What they are, at a deeper level, remains an open question in physics, one noted plainly, without requiring resolution tonight. 5% is already a small number. What that 5% is made of, and how it is distributed, makes the picture more interesting still. Even within ordinary matter, even within every atom of every planet and star and dust cloud in existence, the vast majority of the volume is not occupied by anything. An atom of hydrogen, the simplest and most abundant atom in the universe, consists of a single proton at its center and a single electron moving around it. The proton is real, the electron is real, and the distance between them is enormous by the standards of their own scale. If the proton at the center of a hydrogen atom were enlarged to the size of a marble, the electron would be found, on average, roughly a kilometer away. Between the marble and that distant point, nothing, no material, no substance, no smaller components filling the gap. Just the probabilistic presence of the electron and the electric field holding the whole arrangement together, and otherwise an interior as empty as deep space. This is not unique to hydrogen. Every atom in every element on the periodic table has this structure, a nucleus vastly smaller than the atom itself, and electrons occupying a diffuse shell at proportionally enormous distances. The nuclei of atoms, though they contain nearly all the atom's mass, account for an almost unmeasurably small fraction of its volume. When a hand rests on a table, what is actually happening is that the electrons of the atoms in the hand are repelling the electrons of the atoms in the table. The surfaces never actually making contact in the sense of matter touching matter, because the interiors of the atoms are never in contact with each other. The sensation of solidity is real. The solidity is a different thing from what the sensation implies. When the emptiness inside atoms is combined with the emptiness between atoms in ordinary matter, and then with the enormous volumes of space between stars, and then between galaxies, and then between galaxy clusters, the fraction of the observable universe that is occupied by the actual material of anything at all becomes very small. By some estimates, accounting for all of these nested layers of vacancy, the observable universe is more than 9,999% empty space by volume. What remains? The fraction of a fraction of a fraction that is genuinely occupied by something contains everything that has ever existed and everything that will ever exist in material form. Stars and planets, oceans and mountains. Every organism that has lived on any world, if there are other worlds with organisms, all of it gathered into the thinnest possible film of existence across an almost entirely empty expanse. A grain of sand on a smooth tabletop, very small, a millimeter or two across, pale and rounded, and sitting quietly in the light. This is the sun, not a symbol of the sun, not a metaphor, a physical representation in a scale model where one grain of sand stands in for a star, 4 million kilometers in diameter, a ball of fusing hydrogen so large that 1,000,000 Earths could fit inside it. On that same scale, with that same grain of sand representing the sun, the nearest other grain of sand, representing Proxima Centauri, the closest known star to our own, would not sit a few centimeters away, or a few meters. It would sit several kilometers away. The two grains, on opposite sides of an expanse of open land, nothing between them but air. No other grains of sand for kilometers in any direction, just the two, very small, very far apart, in an otherwise uninterrupted openness. The average distance between neighboring stars in the Milky Way is approximately 4 to 5 light years. Light years are a unit that tends to become abstract quickly, so the grain of sand comparison offers a way back to something felt. The Sun and Proxima Centauri, scaled to grains of sand, separated by several kilometers of nothing. This is the typical spacing between stars in a galaxy that contains hundreds of billions of them. The Milky Way is not dense with stars in the way that a city is dense with buildings. It is a very large, very sparse collection of very small objects, separated by distances that are themselves almost entirely empty. This spacing means that even the Milky Way, a galaxy so large that light takes roughly 100,000 years to cross it from edge to edge, is composed overwhelmingly of space. The stars within it are real and numerous, but they are specks distributed through a disk of almost nothing, and even the gas and dust between them, real as it is and rich in chemistry, is thin by any standard that the word thin can normally be made to carry. A laboratory vacuum on Earth, the most complete absence of matter that human technology can produce, is still denser with stray molecules than much of the interstellar space between stars. The spaces between stars in the Milky Way are emptier than anything on Earth that earns the name empty. There is a comparison that makes the Milky Way's position in the universe concrete in a slightly different way. If the observable universe were compressed to the size of the Earth, not the Earth's orbit, not the solar system, but the Earth itself, a sphere roughly 700 kilometers in diameter, then the entire Milky Way galaxy, with its hundreds of billions of stars, its spiral arms, its dark matter halo, its central bar structure, everything it contains and everything it is, would shrink to the size of a single atom. One atom, not a particularly large atom, an atom that would be invisible to the naked eye, invisible to any microscope that works with visible light, detectable only by instruments that measure at the scale of nanometers. An atom floating inside an object the size of the Earth, and within that atom, everything the human species has ever observed directly, every star whose light has ever fallen on a telescope, every galaxy whose redshift has been measured, our entire observational history contained within something that has no practical size at all. The feeling this comparison produces, if it produces a feeling at all, is not quite like any other. It is not frightening. It is too still for that. It is more like the feeling of a scale drawing that keeps requiring a larger piece of paper, a map maker who begins with a careful rendering of a city block and then must redraw it to include the city, and then the country, and then the continent, and then the planet, each previous drawing becoming smaller on the new sheet until the original block disappears into a point that has no area. The desk the mapmaker works at becomes impossibly small against the map it is trying to contain. The map outgrows the room outgrows the world, and the process, if followed honestly, eventually produces a sheet that includes everything the mapmaker can possibly know about, with the original careful drawings somewhere in it, invisible, exact, still there. The Milky Way as a single atom inside an Earth-sized model of the observable universe. The Sun as a grain of sand on a tabletop, its nearest neighbor grains several kilometers away. The interior of a hydrogen atom nearly entirely empty, its electron tracing its probability cloud a kilometer from the marble-sized nucleus at the center. These are not metaphors chosen for emotional effect. They are scale models, physically accurate representations of ratios that are difficult to hold in ordinary thought, but that become, with patience, simply true. The universe is structured this way. Matter is structured this way. The emptiness is not a flaw in the picture. It is the picture. Somewhere in the plane of the Milky Way, there are regions where hydrogen gas has pooled slowly over millions of years into dense clouds, dark and cold, absorbing the light of everything behind them. These clouds are full of chemistry, molecules assembling slowly in the cold, dust grains acting as surfaces for reactions that would otherwise never occur, the slow, patient accumulation of ingredients. Within those clouds, regions of particularly high density are gradually collapsing under their own gravity, drawing inward, warming as they compress, eventually lighting into stars. The stars, once lit, blow expanding shells of gas and radiation into the space around them, which compress other clouds, which produce more stars, a cycle that has been running for billions of years and continues to run now. Even the empty space between stars is involved in this process. It is the medium through which shock waves travel, the volume through which newly formed elements are dispersed, the space that will eventually be incorporated into future planetary systems and future oceans, and possibly future observers wondering about the emptiness they find themselves surrounded by. A hydrogen atom drifting in the space between two galaxy clusters. Not in a cloud, not near a star, not in the relatively busy environment of a galaxy's interior, in the deep intergalactic space between major structures, where the density of matter is so low that a cubic meter of that space contains, on average, a single atom. One atom, adrift in a cubic meter, surrounded by more of the same in every direction. The atom moves. It has a temperature, technically, in the sense that temperature is a measure of kinetic energy. It moves at some velocity, however slow. It interacts at vast intervals with passing photons. It has been there in some form for billions of years, having drifted gradually out from some galaxy, or been present since the early universe, and it will remain there for billions more, unless the slow expansion of space eventually draws it so far from everything else that even its occasional photon encounters become rare. This is not a lonely image. Loneliness requires something that experiences the absence of company, and atoms experience nothing. It is simply a description of what intergalactic space is like, its actual population, its actual density, its actual character as a physical environment. And what it is like is very empty, in ways that the word empty does not quite prepare for. The best vacuum that has ever been produced in a laboratory on Earth contains trillions of molecules per cubic meter. The best intergalactic space contains one atom. The laboratory vacuum, by the standards of the cosmos, is extremely full. What the emptiness means, physically, is that matter, the 5% of the universe's energy content that consists of protons and neutrons and electrons arranged into atoms and molecules, is gathered into a relatively thin distribution across an enormous volume. The gathering is not random. It follows structure, filaments, walls, clusters, individual galaxies, and within galaxies, the further concentrations into stars and planetary systems. But the gathering, however structured it is, still leaves the overwhelming majority of the available volume unoccupied by anything that would read as solid or gaseous or liquid by any ordinary standard. The universe is, in its dominant character, a great deal of space. The night sky over a flat open plain, well away from any city. The Milky Way arching overhead, its long soft band of light, the accumulated glow of hundreds of billions of stars too far away to resolve individually, their light blending into a pale smear that has been there for every human civilization that has ever looked up at night. This band of light is the Milky Way as seen from within it, a flat disk of stars seen edge on, the galactic center a brighter region towards Sagittarius, the outer arms fading into the dark. It looks substantial. It looks like a structure. From within it, it has the appearance of something vast and full, and it is vast, by the standards of anything that can be seen or touched or crossed by a living thing. By the standards of the universe that contains it, it is the size of a single atom inside the Earth. The scale model does not diminish the Milky Way. Nothing about it is less than it was before the comparison was made. It contains the same number of stars, the same range of planetary systems, the same complex chemistry in its clouds, the same ongoing cycle of stellar birth and death and dispersal. The comparison simply adds a second frame, a context within which the Milky Way's actual size can be placed. Both frames are true simultaneously. The Milky Way is enormous. The Milky Way is, within the context of the observable universe, very small. Both of these things are equally, quietly, correct. There is something useful about the image of the map maker at the desk, continually redrawing the map to include more. The first map is not wrong. The city block is accurately rendered. Every measurement on it is correct. But it is a map of a city block, and there is a city around it, and there is a country around the city, and there is a planet around the country, and there is a solar system around the planet, and there is a galaxy around the solar system, and there is a universe around the galaxy, and the universe contains, by volume, almost nothing except the space between things. The mapmaker's desk keeps growing. The original drawing keeps getting smaller on each new sheet. At some point, the original drawing is indistinguishable from a point. At some point after that, it is smaller than a point. At some point after that, the sheet on which it was first drawn would itself be smaller than a point on the sheet that shows everything the mapmaker can account for. What the mapmaker does not lose in any of these redrawings is the detail of the original. The city block does not become less detailed as the frame widens. It becomes less visible on the larger sheet, but the information is still there, unchanged. The universe contains structures at every scale simultaneously. The atom and the galaxy and the void all present at once, all real, all part of the same physical system, none of them canceling any other out. Dark matter and dark energy make up the remaining 95% of the universe's energy content. These are observational categories, names given to measured effects that do not match what ordinary matter can account for. Galaxies rotate in ways that their visible mass cannot explain. The expansion of the universe is accelerating when unassisted expansion would be expected to slow. Something accounts for the rotation, something accounts for the acceleration. The something that accounts for the rotation is referred to as dark matter. The something that accounts for the acceleration is referred to as dark energy. Beyond the measured effects they produce, neither has a confirmed physical description. Both are real, in the sense that the measurements are real. What they are in themselves is a question that physics continues to work on, without resolution as of the time this is being written. 5%, then, of the universe's energy content is ordinary matter. Of that 5%, the vast majority by volume is empty space within atoms. Of the matter that is genuinely occupied by nuclei and electrons, most of it is gathered into stars and planets and gas clouds that are themselves sparse across the enormous volumes of individual galaxies. Of those galaxies, they are gathered into clusters and walls and filaments, separated by voids that contain almost nothing. And around all of it, 95% of the total energy of the universe consists of forms that cannot be seen or touched or collected into a jar, filling and shaping the space that ordinary matter inhabits. The picture is not of a full universe with some empty regions. It is of an almost entirely empty universe with some structured regions of matter distributed thinly within it. This is what the universe actually is. Not a disappointment, The word disappointment implies that something expected was not delivered, and nothing about this universe was promised to be otherwise. It is simply what the measurements show: a single grain of sand sitting on a table in the quiet. The table is in a room. The room is in a building. The building is in a city, on a continent, on a planet, in a solar system, in a galaxy whose full extent could be crossed by light in roughly 100,000 years. The grain of sand in the scale model is the sun. Several kilometers from here, across open land, is another grain, nothing between them. The two grains are neighbors in galactic terms. The Milky Way contains hundreds of billions more, spread across the same proportional distances, the same proportional emptiness between each one, and the whole of it, all those hundreds of billions of grains, each one a star, each potentially with its own system of orbiting worlds, each producing light and wind and chemistry and the outward push of stellar radiation for millions or billions of years. The whole of it, every grain of sand in the Milky Way, shrinks in the universe to Earth scale model to the size of a single atom. One atom floating inside a sphere the size of the Earth, in a model that represents the full extent of what observation can reach. Everything the Milky Way contains is inside that atom. The atom is somewhere in the Earth-sized sphere, smaller than any instrument sensitive to light can detect. Around it, other atoms, other galaxies, distributed through the model according to their actual positions in the universe, some clustered together in groups, some in long filaments, others more isolated. The model is mostly empty. Even in the model, even at this enormous compression, most of the volume contains nothing at all. This is not a cause for alarm. It is not in any meaningful sense a problem. The universe was not designed for density, and there is no expectation it should have been. What it is was not designed for density, and there is no expectation it should have been. What it is structured in a particular way, a way that turns out, when measured carefully, to be almost entirely characterized by emptiness, with matter gathering along specific patterns within that emptiness, and within that matter, further patterns of gathering and vacancy, all the way down to the scale of the nucleus and the electron. The night sky is dark because the distance between stars is real. The darkness is not background. It is the dominant feature. The light, the stars, the Milky Way, the galaxies visible through telescopes is the exception, the thin gathering, the small fraction. The darkness between the stars is not the absence of the picture. It is the picture, and the stars are the detail within it. The Milky Way, reduced to the size of a single atom inside a sphere, the size of the Earth, sits quietly in that imagined model, complete, detailed, containing within it every star and planet and cloud of cold gas and warm nebula, an expanding remnant of an old explosion that has ever been observed or ever will be observed from within it. The atom is very small, the sphere is very large, and everything that has ever been known about the universe, from within this particular vantage point, fits inside an atom that has no practical size at all, and is still there, exact and complete and undiminished, floating in the wide-open interior of the model, the space around it mostly nothing, as it always has been, as the universe, in its quiet and unhurried way, continues to be. Heinrich Wilhelm Olbers was by profession a physician. He ran a practice in Bremen, saw patients through the days, and reserved the nights for the sky. His observatory was built into the upper floor of his own house, which meant that the instruments and the lenses and the careful notebooks were never far from wherever he happened to be standing, and the habit of looking upward was not something he set aside when the working day was done. On the night of an ordinary autumn evening in 1823, with a candle burning low beside his desk and the window open to the dark, he began writing out a question that had been forming in his mind for some time. The question was not complicated. It did not require elaborate mathematics to state, and it would have been intelligible to anyone who had spent even a few quiet hours watching the night sky. He wanted to know why, if the universe was infinite and uniformly scattered with stars in every direction, the night sky was dark at all. It seems at first like a question with an obvious answer. The sky is dark at night because the sun has set. The stars are distant, and distance makes things dim. Both of these responses feel sufficient until a person sits with them long enough to find the seam where they come apart. The first dissolves immediately. The question is not why the sun is absent from the night sky, but why the stars collectively fail to compensate. The second takes a little longer to unravel, but it does unravel, and when it does, the question underneath turns out to be considerably more interesting than it first appeared. Distance does make individual stars dimmer. A star twice as far away delivers 1/4 of the light. That much is straightforward geometry, the same inverse square law that governs any radiating source in open space. But in an infinite universe, the number of stars at twice the distance is 4 times as great, because the surface area of a sphere grows with the square of its radius, and more distant shells of space contain proportionally more stars. The dimming of each star and the increasing number of stars at greater distances cancel each other out precisely. Every shell of space contributes the same total brightness to the sky as every other shell, regardless of how far out it lies. And if there are infinitely many such shells, the sum is infinite. The night sky, on this reasoning, should blaze with light in every direction, not dim scattered points, but a continuous, undifferentiated, searingly bright surface, every line of sight eventually terminating at the face of a star. There would be no darkness, no depth, no sense of looking outward into anything, only the flat, featureless light of an infinite stellar interior pressing in from every direction at once. Olbers was not the first person to notice this. Johannes Kepler had observed in the early 17th century that the darkness of the night sky was itself an argument against the universe being infinite. If it extended without boundary, he reasoned, the sky would be as bright as the sun. Edmund Halley, better known for the comet that bears his name, also considered the problem in the early 18th century, and was not fully satisfied by the answers available to him. The question drifted through astronomical thought for 2 centuries without quite being resolved, attached to different names at different times, finding no permanent home until Olbers gave it the formal treatment in his 1823 paper, and by an accident of historiography, kept his name on it afterward. What Olbers proposed as a resolution was absorption. If some medium existed between the stars, some diffuse material filling the interstellar spaces, it might intercept the light of distant stars before it reached the eye, limiting the effective depth of the sky's luminosity and restoring the darkness. The proposal was not unreasonable, given what was known at the time, but it contained a flaw that would be identified later. Any medium dense enough to absorb the cumulative light of an infinite universe would, over enough time, heat up to the same temperature as the stellar surfaces themselves and begin re-radiating that energy. The darkness would return eventually, yes, but only briefly. The absorbing medium would become a glowing medium, and the sky would brighten again on a longer timescale. Absorption postpones the problem. It does not dissolve it. Olbers at his desk did not know this. He published his paper, made his proposal, and the problem moved forward under his name into the 19th century, where it accumulated more attention and more proposed solutions, none of them fully satisfying, the question persisting with a quietness that suggested something fundamental had not yet been said. The something fundamental, when it was said, came from an unexpected source. In 1848, 25 years after Olber's paper and 7 years before his death, a writer in Baltimore published a long prose work that he described not as a poem or a story, but as an essay, a cosmological meditation he called Eureka. The writer was Edgar Allan Poe, known primarily for tales of horror and verse of considerable darkness, and the work he produced in 1848 does not resemble his fiction in any obvious way. Eureka is ambitious and digressive, and not uniformly successful as a piece of scientific reasoning, and when it was published, it was received with more puzzlement than admiration. Poe himself considered it the greatest work of his career. Most readers set it aside, but somewhere inside its long, wandering argument about the origin and structure of the universe, Poe wrote a passage that addressed the dark night sky problem directly, and his answer, stated in the plain prose of a careful thinker rather than the mathematical language of a physicist, was essentially correct. The stars are not infinite in their number, Poe wrote, or if they are, light from the most distant of them has simply not had time to reach us. The universe, he suggested, had not always existed. It had a beginning, a moment before which there was nothing, and the finite time that had elapsed since that beginning placed a natural limit on how far light could have traveled to reach any given observer. Stars beyond a certain distance were dark, not because anything blocked their light, but because their light had not yet arrived. The darkness between the stars was not an absence, it was a distance that time had not yet finished crossing. Poe offered this as intuition rather than calculation. He did not have the physics to formalize it, and Eureka contains genuine errors alongside its genuine insights. The scientific community of 1848 had no particular reason to take its cosmology seriously, and largely did not. For most of the following century, the passage about the dark sky sat inside a text most readers associated with strange fiction rather than astrophysics, unremarked upon by the people positioned to evaluate it properly. The idea itself that the universe had a finite age, and that this age explained the darkness of the sky, would not gain serious scientific traction until the 20th century, when the evidence for cosmic expansion and a definite beginning accumulated to the point where it could no longer be set aside. When it did, and when people looked back through the literature for earlier anticipations of the idea, they found the passage in Eureka and noted it, a little surprised, as a case of genuine intuition arriving decades ahead of the science that would eventually confirm it. It is worth dwelling for a moment on what the correct resolution actually says. The night sky is dark, not because the universe is finite in its extent, though it may or may not be. It is dark because the universe has a finite age. The key figure is approximately 8 billion years, the time that has elapsed since the Big Bang, which is the name given to the initial state from which the observable universe emerged. Light travels at a fixed speed, roughly 300,000 kilometers per second, and in 8 billion years, it covers a fixed distance, which defines a sphere around any observer beyond which no light has yet had time to arrive. Stars and galaxies beyond that sphere may exist. The universe almost certainly extends well past the limits of what any observer can detect, but their light has not reached us. They contribute nothing to the brightness of our sky. Every line of sight that would otherwise terminate at the glowing surface of a distant star instead terminates at nothing, because the star, however real, is outside the range of what 13.8 billion years of travel can deliver. The resolution is quiet in the way that correct answers to genuinely hard problems sometimes are. Nothing exotic is required. No special medium, no unusual physics, no modification of how light behaves. Only the recognition that the universe has not always existed, that time has been running for a definite duration, and that light has been traveling for the same duration, and that the combination of those two facts produces a natural horizon beyond which nothing is yet visible. The sky is dark because the universe is young, young at least relative to what it would need to be for the light of every star in an infinite cosmos to have completed its journey. There is a second factor at work alongside the universe's age, and it deepens the darkness in a way that Poe could not have anticipated, and that Olbers had no way to account for. The universe is not static. It has been expanding since the Big Bang, space itself stretching in all directions, carrying galaxies away from one another at speeds that increase with distance. For nearby galaxies, this recession is gentle enough that it has little effect on the color of their light. For very distant galaxies, those near the edge of the observable universe, the recession is so rapid that the light they emit is stretched dramatically in the process of crossing the expanding space between source and observer. A photon that began its journey as visible blue light, the kind a human eye can register, might arrive after billions of years of travel as a long, slow infrared wave, or deeper still into the microwave range, its original color stretched entirely out of the visible spectrum. The galaxy it came from may be luminous and full of stars, but its contribution to the brightness of the sky, as seen by human eyes, is precisely zero, because the signal it sends has been translated into a language the eye does not speak. This process is called cosmological redshift, and it operates on every photon crossing large cosmic distances. The most distant light sources in the universe are not dimly visible at the edge of human perception. They are invisible in visible light entirely, their emissions shifted wholesale into wavelengths the eye cannot detect. Instruments can find them, radio telescopes, and infrared arrays tuned to the frequencies where that stretched light actually arrives. But the naked eye, looking up from a dark field on a clear night, receives nothing from them. They contribute darkness rather than light, not because they have no light to give, but because the light they give has been stretched past the threshold of what the eye can register. The combined effect of the universe's finite age and the redshifting of distant sources is a night sky that is not merely dark, but productively dark, dark for specific physical reasons that carry information about the structure and history of the cosmos. Every dark patch between the stars is dark for one of two reasons, or both. Either nothing luminous lies along that line of sight within the reachable volume, or something luminous does lie there, but its light has been stretched beyond visibility during the crossing. The sky is dark because time is finite. The sky is darker still because space is expanding. Olbers did not have either of these resolutions available to him. He was working in a period when the universe was assumed to be infinite, static and eternal, a stage already constructed, already populated, simply existing without a beginning or an end. On those assumptions, the darkness of the night sky was genuinely paradoxical, a persistent discrepancy between what the mathematics predicted and what the eye observed. It was not resolved in his lifetime. It was not resolved in the lifetime of the generation that followed him. The paradox outlived the assumptions that produced it, and by the time it was properly resolved, In the 20th century, the assumptions themselves had been replaced by something considerably more interesting. On a cold night, standing outside the city in a field where the lights of buildings do not reach, the sky overhead presents itself without interference. The Milky Way arches from horizon to horizon as a soft, smeared band, brighter in some places than others, its structure suggesting depth without revealing it clearly. The stars individually are sharp and still, set against a background that is, between them, genuinely and deeply black. This is the sky as Olbers saw it, as Kepler saw it, as Poe saw it from whatever window in Baltimore he happened to be standing at when the ideas in Eureka were forming. The same view, the same darkness, the same question sitting quietly inside it. Why dark? The question does not feel urgent on a still night. It feels more like a natural feature of the scene. The darkness is simply the sky, and the sky is simply there, and the mind at rest does not press very hard on the word simply, but the darkness is not simple. The darkness is a record of the universe's age, written across the entire overhead surface of the night, in the only medium available, the absence of what would otherwise be there. Every unlit square of sky is a timestamp, a marker indicating that 8 billion years, has not been quite enough time for the light from that direction to complete its crossing. The paradox that Olbers formalized, and that Kepler glimpsed, and that Poe intuited, is sometimes described as a problem that has been solved, and in one sense it has. The physics is settled, the key factors are known, the resolution is documented and taught. But the experience of standing under a dark sky and holding the knowledge alongside the view does not feel like problem solving. It feels more like the particular quiet that comes after a long question is answered, and the mind, released from the effort of working on it, settles into something slower and wider. The sky is dark. It is dark because the universe had a beginning. Light from the most remote sources is still in transit, still crossing the vast distances between origin and eye, still arriving, in some cases after journeys measured in billions of years. Some of what departed in the earliest ages of the universe has not reached here yet. Some of what is traveling toward this point right now will not arrive for eons. What does arrive, at the edge of visibility, has often spent so long in transit that the universe it departed from no longer exists in the form it had when the journey began. A photon leaving a young galaxy in the early universe crosses expanding space, passes through regions that will later accumulate into galaxy clusters, through voids that will later deepen as matter drains away into the surrounding filaments, arrives at a telescope or an eye. That is, it's located in a galaxy that did not exist when the photon began moving. The photon is older than the Milky Way. It has crossed a universe that kept rearranging itself around it during the entire duration of the crossing. And when it arrives, if it arrives in visible wavelengths, the eye that receives it sees a faint point of light, so distant it barely registers as distinct from the general darkness. If it arrives in stretched wavelengths, infrared, microwave, the eye sees nothing at all. The photon completes a journey of billions of light years and arrives invisibly, adding its faint energy to the background without any perceptible change in the darkness. The sky stays dark. The resolution stays complete. There is something comfortable about this when it settles in. Not the vastness. The vastness does not settle in easily. The numbers are too large for that, but the neatness of the fit between question and answer. Olbers noticed a discrepancy. Many people after him noticed the same discrepancy and proposed various resolutions, most of which failed on examination. A writer not particularly known for scientific reasoning proposed a resolution in 1848 that was essentially correct and was mostly overlooked. The correct resolution eventually emerged from the physics and was confirmed by observation, and when it was complete, it turned out to require nothing unusual, only a recognition of what the universe actually is, as opposed to what it had been assumed to be, a place with a history, a place that began. The fact that the sky is dark is on this account not a failure of the stars to illuminate. It is the universe communicating something true about itself in the simplest available medium, not light, but the absence of light at the distances where light has not yet had time to travel. Not blazing undifferentiated brightness, but a dark field with scattered points, the darkness itself doing the communicating, the message written across the whole overhead sky every night without interruption, available to anyone who has ever looked up and wondered why. Poe, writing in 1848, did not have the tools to calculate the age of the universe. He did not have access to the measurements that would eventually confirm cosmic expansion, or the concept of a photon, or any of the formal structure of modern cosmology. What he had was the capacity to hold a genuine question at arm's length and look at it calmly, to notice that an eternal universe and a dark sky were in tension with each other, and to propose that the tension might be resolved by the universe not being eternal. The proposal was intuitive, imprecise, and correct in its essential logic. It appeared in a work of prose that its author considered his greatest achievement, that the scientific community largely ignored, and that most readers filed under fiction and moved past. The idea it contained kept traveling the way photons do, until it arrived somewhere that could receive it. The specific image that remains, from all the ways the paradox can be described and all the technical mechanisms through which it is resolved, is a simple one: a photon departing a galaxy in the early universe, when the cosmos was younger and hotter and densely packed with forming structures, beginning a journey across expanding space, setting out in the visible wavelengths, blue perhaps, or near ultraviolet, the light of young hot stars blazing in a galaxy that has just begun to form, crossing the first billion light years, the second, the universe expanding around it the whole time, space stretching, the photon's wavelength stretching with it, the blue shifting toward green, then toward yellow, then toward red, then into the infrared, then further still. 10 billion years of travel, 12 billion. The galaxy it departed from long since evolved into something different. Cooler stars, more dust, a different morphology. The original blue brilliance faded into a quieter middle age. The photons still moving, still crossing, arriving finally in the vicinity of a world with instruments sensitive enough to detect it. No longer visible blue, but a long, slow microwave pulse, its original wavelength stretched by the expansion of the space it crossed into something entirely beyond the range of any eye. It arrives. It is detected. It adds its small energy to the accumulated signal of a radio telescope pointed in the direction it came from. The sky, to any observer standing outside and looking up, remains dark in that direction. The photon completed its journey invisibly, having spent its visible wavelengths in the crossing, arriving as a whisper in a frequency the eye does not register. The night sky is dark because of photons like this one, not absent, not blocked, not absorbed into anything that then re-radiates at stellar temperatures, but stretched, translated, shifted into a register that the eye cannot read. The darkness is not empty. It is full of messages written in wavelengths the eye cannot see, arriving from distances the mind only approximates, carrying information about the universe in its earliest centuries. information still in transit after billions of years of traveling, information that accumulates in the instruments of observatories and slowly, carefully tells the story of what the universe was like long before any of the structures it currently contains had formed. The dark sky at night is all of this at once. The darkness between the stars is the universe's age, recorded. It is the expansion of space, written in shifted wavelengths. It is the finitude of the time since everything began, expressed as the simple absence of light from sources too far away to have reached here yet. And it is, somewhere inside all of that, the question that Olbers wrote down at his desk in Bremen, still turning slowly, still open in the particular way that questions remain open when they have been answered correctly. But the answer is large enough that sitting with it requires a certain patience. The answer is patient too. It has been there since the night sky has existed, written across every dark hour on every clear night, waiting not to be discovered, but to be recognized as what it already was, not an absence, but a message, written in the only medium a stretched and ancient photon has available to it, arriving quietly, arriving now, arriving in wavelengths that no eye can read, and that carry, in their long, slow oscillation, something true about the world as it was when the light first set out. A printed map of the nearby universe, when spread across a large table, does not look the way most people expect. There are no clean circles of planets, no evenly spaced pinpricks of light arranged in orderly rows. What it shows instead is something closer to a cross-section of foam, clusters of dots bunched along thin curving lines, the lines themselves tracing long arcs through wide regions that contain almost nothing at all. The dense parts form threads and nodes, bright with the compressed positions of thousands of galaxies, and the spaces between them stretch out in pale, nearly empty expanses that are not blank from lack of data, but genuinely, structurally, almost devoid of galaxies. Hold the map at arm's length, and it resembles, more than anything else, the interior wall of a soap bubble seen through a microscope, a delicate skeleton of material surrounding chambers of near emptiness, the whole thing far more whole than substance, the pattern repeating in every direction the survey reaches. This is what the large-scale structure of the universe looks like. Not a smooth distribution of galaxies spread evenly through space, which is what might be expected if matter settled uniformly after the Big Bang, but something with texture and architecture, a cosmic web of dense galaxy-bearing filaments and enormous nearly empty regions. The filaments are where the galaxies live, strung along gravitational pathways like beads along a wire. The regions between them, the vast chambers inside the foam, are called voids. They are not accidents or gaps in the data. They are structural features of the universe, as real and as mappable as the filaments themselves, and in terms of sheer volume, they dominate. The universe, at its largest scales, is mostly void with threads of galaxies running through it, the way a sponge is mostly air, with thin walls of material running through it in every direction. The voids are quiet regions, not silent in the sense of containing no movement. Matter does move through them, and the rare galaxy that drifts into a void continues on its path. They are quiet in the sense of density. Where a typical region of space along a filament might hold dozens of galaxy clusters within a relatively compact volume, a void holds almost none. Statistical models built from the measured distribution of galaxies in surveyed regions of sky predict how many galaxies any given volume of space should contain, based on the overall average density of the universe. When those models are applied to the large empty chambers of the cosmic web, The predictions return numbers in the hundreds or thousands. The actual counts return single digits or none at all. One particular void became a subject of careful attention in 1981 when a team of astronomers led by Robert Kirshner completed a survey of galaxy positions in the direction of the constellation Bedtime. Kirshner and his colleagues were conducting a redshift survey, measuring the velocities at which galaxies appeared to be moving away from Earth, which served as a proxy for their distances, allowing the researchers to build a three-dimensional picture of the galaxy distribution in that part of the sky. What the data showed when assembled was a region spanning approximately 330 million light-years in diameter that contained only a handful of galaxies, where the statistical models predicted thousands. The void simply sat there in the data, a hole of near absence in the fabric of the galaxy distribution, larger than anything the survey team had been expecting to find. Kirshner described the discovery as the most dramatic feature they had encountered in the survey, a gap so large and so empty that it demanded some explanation for why matter had arranged itself around it rather than through it. The Bedtime's void, as it came to be known, is not unique. The cosmic web contains many such regions, large and small, distributed throughout the observable universe. But the Bedtime's void holds a particular place in the history of observational cosmology, because its scale, at the time of its discovery, exceeded what most theoretical models of structure formation had predicted was possible. A region 330 million light-years across, nearly emptied of galaxies, required explanations that touched on the deepest questions about how the universe had evolved, how matter had moved over billions of years, what forces had pushed it toward the filaments and away from the voids, and what the distribution of unseen mass looked like in the spaces where galaxies were not. To cross the Bedtime's void at the speed of light would take 330 million years. Traveling that distance through that near emptiness, the traveler moving at the maximum speed the universe permits would encounter only occasional, widely scattered galaxies, not the dense clustering of a filament, not even the modest concentration of an average region of space, but something closer to true isolation, the occasional dim smear of a galaxy appearing against a background that is almost uniformly dark. The word almost matters. The void is not entirely empty. A handful of galaxies inhabit it, their positions scattered without any clear clustering, as if each one had wandered in from the surrounding web and found itself without neighbors. The void is one of the largest known structures in the observable universe, and it is defined almost entirely by what it lacks. The filaments that bound regions like the Bedtime's void are themselves extraordinary objects. They are not solid structures in any ordinary sense. Nothing about them has a hard edge or a surface. They are concentrations of matter in three-dimensional space, rivers of galaxies flowing along gravitational pathways that were established in the early universe when slight variations in density began to amplify under their own gravity. Along these filaments, galaxy groups and clusters have accumulated over billions of years, their positions tracing the underlying pattern of mass distribution like trees growing along the banks of a river. The filaments connect nodes, particularly dense intersections where multiple filaments converge, and the nodes hold the most massive galaxy clusters in the universe, places where thousands of galaxies are packed into a relatively compact region of space. The Milky Way belongs to a filamentary structure that was identified and mapped in careful detail by a team of astronomers who published their work in 2014. What they found was that the galaxy sits within a supercluster of enormous extent, a region of space encompassing roughly 100,000 galaxies, stretching approximately 520 million light-years from one edge to the other, with a combined mass equivalent to around 100 quadrillion times the mass of the Sun. This structure, which the team named Laniakea, a Hawaiian word meaning immeasurable heaven, is not defined by a simple boundary. Its shape is traced by the gravitational flows of matter along its filaments, the way galaxies within it are moving, the directions they are drifting as they respond to the collective gravitational pull of the whole structure, the slow rivers of matter that reveal where the mass is concentrated and where the gravitational influence of the supercluster ends. Laniakea is best understood not as a rigid object, but as a drainage basin. Just as water on a landscape flows downhill toward a common low point, matter within Laniakea moves along gravitational gradients toward a region of concentrated mass near its center, a feature known as the Great Attractor. The galaxies of Laniakea are not stationary. They are flowing very slowly by any human timescale, but detectably so by careful measurement along pathways that converge toward this central region. The Milky Way is part of this flow. Its motion through space is not simply the expansion of the universe carrying it away from other galaxies in every direction. It has an additional velocity component, a drift along the filament toward the deeper gravitational basin of the supercluster. The galaxy is in motion within a structure that is itself slowly reorganizing, and both of those things are true simultaneously, happening at scales and time scales that bear no resemblance to anything that can be directly perceived. From within the Milky Way, none of this structure is visible. The galaxy sits near one of Laniakea's outer banks, a quiet position toward the edge of the supercluster, and the distances involved are so large that no instrument currently in existence can photograph the whole structure in a single observation. Its shape is known not from images, but from measurements, from the velocities of thousands of individual galaxies, each one measured separately, their motions assembled into a coherent picture of the gravitational field that governs them all. The map of Laniakea is a velocity map, a picture drawn from the direction and speed of motion rather than from light alone, and it reveals a shape that is complex and asymmetric, not a sphere, but an irregular web of flowing mass, with a denser spine running through it and thinner branches reaching outward. The question of why the universe has this filamentary structure at all, why it is not smooth, why galaxies cluster along threads and leave vast voids behind, leads to one of the less directly observable components of the universe's total mass and energy. Ordinary matter, the kind that forms stars and planets and dust clouds, interacts with light. It absorbs it, emits it, scatters it. This makes it visible to instruments that detect electromagnetic radiation across every wavelength, from radio waves to gamma rays. But ordinary matter accounts for only a fraction of the gravitational mass that simulations and observations suggest must be present for the cosmic web to have formed in the way it has. Something else must supply the gravitational scaffolding along which ordinary matter has arranged itself. Dark matter is the name given to this unseen component. The name is straightforward in its description of the problem. It is matter in the sense that it has mass and gravitational influence, but it is dark in the sense that it does not interact with electromagnetic radiation in any detected way. It does not emit light, absorb light, reflect light, or scatter it. The only evidence for its presence comes from its gravitational effects, the way it bends the paths of light passing nearby, the way it holds galaxies together more tightly than their visible mass alone could account for, and the way that computer simulations of structure formation in the early universe produce a cosmic web resembling the observed one, only when dark matter is included in the initial conditions. The Millennium simulation, completed in 2005, by a consortium of researchers at institutions across Europe and the United States, was an attempt to model the formation of cosmic structure from the conditions of the early universe to the present day within a cubic volume of simulated space, 2 billion light years on a side. The simulation tracked the gravitational interactions of more than 10 billion particles representing dark matter, following their movements through simulated time as the universe expanded and matter clumped under its own gravity. What emerged over the course of the simulated billions of years was a cosmic web, dark matter halos condensed first along invisible threads, their positions determined by the slight density variations present in the initial conditions. Ordinary matter, represented separately, accumulated in the gravitational wells that the dark matter halos created. Galaxies appeared one by one along the filaments, lighting up like slow sparks tracing a pre-existing skeleton that was itself invisible, a ghost web of dark matter defining the pathways along which visible matter would eventually gather. The match between the simulation's output and the observed large-scale structure of the real universe was and remains one of the strongest pieces of evidence that the broad picture of cosmological structure formation is correct. The filaments in the simulation align with the filaments in the observed universe. The voids in the simulation correspond to the voids in the survey data. The mass function of galaxy clusters, how many clusters of each mass exist, follows the same distribution in the simulation as in observation. Without dark matter in the initial conditions of the simulation, the structure that forms does not match what the universe actually contains. The filaments are too diffuse, the clusters too sparse, the voids too occupied. The presence of dark matter, whatever it physically is, appears to be necessary for the universe to have developed the structure it currently shows. The scaffolding metaphor is useful, but requires some care. Dark matter does not simply provide a pre-built framework that ordinary matter then fills in like plaster poured into a mold. The relationship is dynamic and evolving. Dark matter and ordinary matter interact gravitationally with each other and independently respond to the overall expansion of the universe, and the structures that emerge from this interaction develop over billions of years in a process that is still ongoing. The cosmic web is not finished, and voids are still growing as matter continues to drain toward the filaments. Filaments are still deepening as additional matter flows along them toward the nodes. Galaxy clusters at the intersections of filaments are still accumulating new members, their masses still growing as smaller groups fall in from the surrounding web. The universe is in motion at every scale, all at once, though the time scales involved make every individual moment appear frozen by comparison to any human frame of reference. The mapping of these structures has been one of the major undertakings of observational astronomy over the past several decades. The technique that made large-scale mapping possible is the same one Kirshner's team used in 1981, measuring the redshifts of large numbers of galaxies, converting those redshifts to distance estimates, and assembling the resulting three-dimensional distribution into a picture of where the galaxies actually are in space. The challenge is one of sheer volume. Not every galaxy can be measured individually, and the surveys must balance the number of galaxies they include against the sky area they cover and the precision of their measurements. Early surveys measured hundreds or thousands of galaxies. More recent ones have measured tens of millions. The Sloan Digital Sky Survey, which began operations in 2000 and continued through multiple phases over the following decades, produced one of the most comprehensive maps of the nearby universe ever assembled. Using a dedicated telescope at Apache Point Observatory in New Mexico, The survey measured the spectra and positions of hundreds of millions of celestial objects, building a three-dimensional picture of galaxy distribution across a substantial fraction of the sky. The data from the Sloan survey has been used to identify and characterize the large-scale structure of the nearby universe with a precision not previously possible, revealing the cosmic web in finer detail and over larger volumes than earlier surveys had been able to reach. Within the Sloan survey data, a structure emerged in 2003 that extended what was already known about the scale of cosmic filaments. A concentration of galaxy clusters identified in the full three-dimensional distribution of the survey's galaxy catalog stretched across the sky in a single connected structure approximately 137 billion light-years in length. The researchers who identified it called it the Sloan Great Wall. It was, at the time of its announcement, the largest known structure in the observable universe, a single filament of galaxy clusters, so long that it spanned a distance more than 10 times the diameter of the Boots void, a thread of accumulated mass visible only because the survey had measured the distances to hundreds of thousands of individual galaxies and assembled their positions into a coherent three-dimensional map. The Sloan Great Wall is not exceptional in the way a single remarkable object is exceptional. It is not the densest concentration of matter, not the most luminous region, not the place where the most dramatic astronomical events are happening. What makes it significant is purely its length, the sheer linear extent of a connected structure. The fact that matter has arranged itself, under the influence of gravity and dark matter, and the geometry of the early universe's density fluctuations, into something 37 billion light-years long, that hangs together as a recognizable feature in the galaxy distribution. It is a brushstroke across a very large canvas, visible only in 3 dimensions, invisible in any 2-dimensional projection of the sky, no matter how sensitive the telescope used to observe it. To understand why it was invisible before redshift surveys existed, consider what it looks like from Earth without depth information. The galaxies that make up the Sloan Great Wall are spread across a patch of sky, but so are all the other galaxies in the survey: foreground galaxies, background galaxies, galaxies at every distance from the nearest to the most remote. Without knowing which galaxies are at the same distance, and therefore potentially part of the same structure, the Great Wall disappears into the general field. It becomes indistinguishable from the random scatter of galaxies projected onto the 2-dimensional surface of the sky. It is only when the 3rd dimension is added, when each galaxy's distance is known, and the distribution can be examined in depth, as well as in width and height, that the wall resolves from noise into structure, from scatter into pattern. The universe hid its largest feature by making it invisible from any vantage point that lacks depth. The technique of redshift mapping involves measuring the spectrum of each galaxy's light and finding how far its spectral features have been shifted toward longer wavelengths by the expansion of space. More distant galaxies are receding faster, and their light is redshifted more. The redshift therefore serves as a distance indicator, imprecise in various ways that astronomers have carefully quantified and corrected for, but reliable enough over large numbers of galaxies to reveal the 3-dimensional distribution with considerable fidelity. A redshift survey is, in a sense, a depth map of the universe, a way of measuring how far away things are by asking how fast they appear to be moving, and using that to reconstruct where they actually sit in 3-dimensional space. Running such a survey requires measuring the spectra of very large numbers of galaxies, one by one. The Sloan survey used a spectrograph capable of measuring the spectra of hundreds of galaxies simultaneously, but the fundamental requirement was the same. For each galaxy, light had to be collected, dispersed into its component wavelengths, and the positions of known spectral features had to be identified and measured with sufficient precision to yield a useful distance. Multiplied across hundreds of millions of objects, this process produced a database of galaxy positions that has been used by researchers around the world for purposes well beyond the search for large-scale structure. But the structure it revealed was among the most striking of its early results. Since the announcement of the Sloan Great Wall in 2003, subsequent surveys and analyses have identified structures that rival or exceed it in scale, though the definition of what constitutes a single connected structure involves methodological choices that affect the resulting size estimates. Some analyses have identified features spanning several billion light-years, though the community has not uniformly accepted all such identifications as representing genuinely connected gravitational structures, rather than chance alignments or artifacts of the analysis method. The question of what counts as a structure at these scales touches on fundamental issues in cosmology, including a theoretical expectation, sometimes called the cosmological principle, that the universe should look roughly the same from any vantage point and in any direction when viewed at large enough scales, with no structure extending beyond a certain maximum size. Structures at or beyond the predicted limits of this principle are watched carefully by theorists, though the current observational evidence does not clearly require abandoning the principle so much as it continues to refine the scales at which it applies. The cosmic web is, in this sense, a living subject, not yet fully mapped, not entirely understood, its largest features still being measured and debated. The surveys that revealed the filaments and voids have been succeeded by larger and more precise surveys, and each generation of data has added detail to the picture without simplifying it. The foam structure that appears in the printed maps is not a complete picture, but a snapshot of an ongoing process, a universe arranging and rearranging itself under the influence of forces that operate across distances so vast and over timescales so long that the arrangement visible today is only one frame in a sequence that began when the universe was a fraction of its current age and will continue long after any current state of affairs has been superseded. Within that ongoing arrangement, the voids remain the dominant feature by volume. They are not nothing. They contain a sparse scattering of galaxies, a thin distribution of ionized gas too diffuse to detect by most methods, and the same dark matter that pervades all of space, though at densities lower than those found along the filaments. They are not empty in any absolute sense. Emptiness of that kind exists nowhere in the universe, where even the most rarefied regions contain something. But the voids are close enough to empty to represent a genuine departure from the average density of the universe, a kind of gravitational shadow cast by the filaments that drain matter away from them and toward the nodes. A galaxy that finds itself deep within a large void. There are some, scattered through the interior of even the largest ones, exists in a particular kind of isolation. Its nearest neighboring galaxy may be tens or hundreds of millions of light-years away, rather than the few million that would separate it from its neighbors in a filament. The gravitational environment around it is unusually quiet. The tidal forces from nearby mass concentrations unusually weak. Such void galaxies have been studied in detail by observational astronomers because their relative isolation makes them interesting test cases for theories of galaxy evolution. The question being whether a galaxy that has evolved in the near absence of close neighbors differs systematically from one that has grown up embedded in a cluster or along a busy filament. The answer, as surveys of void galaxies have established over recent decades, is that void galaxies do differ. They tend to be bluer and lower in mass than their counterparts in denser environments, more likely to be actively forming new stars, less likely to have undergone the mergers with other galaxies that reshape and enlarge galaxies over time. The void environment, in other words, leaves a measurable imprint on the galaxies within it, not because the void does anything to them actively, but because of the absence of things that would otherwise happen. The mergers do not occur because there are no nearby galaxies to merge with. The tidal forces do not reshape the galaxy because there are no massive nearby structures to exert them. The void shapes its galaxies through what it lacks, the way a quiet room shapes what a person does in it, not by applying pressure, but by removing it. The large-scale structure of the universe, when held at sufficient remove to see the whole pattern at once, is one of the most geometrically striking things that modern astronomy has produced. A three-dimensional map of the galaxy distribution within a few billion light-years of the Milky Way, rendered in a visualization that preserves the full depth and extent of the survey data, shows something that does not resemble any human-made structure and does not correspond to any intuitive picture of how matter distributes itself. It is too intricate to be random, too open to be solid, too large for any single scale to encompass comfortably. The nodes glow at the intersections of filaments, the filaments stretch between them in great arcs, and the voids open between the arcs like the spaces inside a frozen wave. The map does not show the dark matter directly. It cannot. Dark matter leaves no mark on any telescope. What the map shows is ordinary matter, the galaxies whose light the surveys measured, arranged along the outlines of something that cannot itself be seen. The filaments in the map are like riverbanks without a visible river, the shape of a flow that has left its mark on what sits along its edges. The dark matter scaffolding is inferred from the distribution of the ordinary matter it has influenced, and the inference is tight enough and consistent enough across enough independent observations that its reality is not seriously in question within the scientific literature, even though its physical nature remains an open and actively investigated problem. Between the filaments and the voids, between the galaxy clusters and the near emptiness, the universe maintains a kind of balance, not a static one, but a slow dynamic equilibrium between gravity drawing matter together and the expansion of space carrying everything apart. The filaments grow denser as matter flows along them. The voids grow emptier as matter drains away. The expansion continues, regardless of both processes, stretching the distances between clusters and superclusters, even as local gravity fights to hold them together. At the very largest scales, the ones that approach the size of the observable universe itself, the expansion wins, and the most distant structures recede beyond any hope of gravitational interaction. But at the scales of superclusters and filaments, gravity still shapes what happens, and the slow organization of matter into the cosmic web is still proceeding, still adding to the pattern that began when the universe was very young, and the density variations that seeded all of this were less than 1 part in 100,000. The Sloan Great Wall stretches its 37 billion light-years across a portion of that pattern, one long filament among many, identified because a survey measured the distances to hundreds of thousands of galaxies and assembled the measurements into a map. And the map revealed, in its three-dimensional arrangement, something that no photograph of the sky had ever shown. It was hidden not by any lack of telescopic power, but by the simple absence of depth. The galaxies were always there, their light always reaching Earth, their positions always waiting in the data. The wall became visible only when someone thought to ask not just where in the sky each galaxy sat, but how far away it was, and then to look at all those distances together and see what shape they made. The largest known structure in the observable universe at the time of its discovery was hidden in plain sight inside a two-dimensional photograph, invisible until the third dimension was added, and then impossible to miss. That discovery, and the wider practice of three-dimensional redshift mapping that produced it, is the reason the cosmic web is known at all. The foam that appears in the maps, the filaments and voids, and the great organized emptiness of the universe at its largest scales is not something that could have been predicted from the night sky alone or inferred from the positions of stars visible to the naked eye. It required the systematic measurement of distances to millions of objects, a technology and a patience that accumulated over decades, and a willingness to treat the three-dimensional distribution of galaxies as a subject worth mapping for its own sake. The universe, it turned out, had arranged itself into something with structure at every scale above a certain threshold, and the structure at the largest scales was one of the last things to be seen clearly, hidden by its own enormity until the surveys grew large enough to contain it. A printed map of the universe, spread across a table, still needs to be looked at from a certain distance before the pattern resolves. Hold it too close, and the individual galaxies scatter across the page without apparent order. Step back far enough and the filaments emerge, the voids open between them, and the foam-like structure of the whole becomes visible as a pattern rather than a scatter. The universe hid this structure, not inside any single remarkable object, but inside the arrangement of millions of unremarkable ones, each one contributing one small position to a picture that required all of them to become coherent. Each one a point in a distribution that only makes sense when the distribution is complete enough to show the shape it has been tracing all along. Between one star and the next, there is no clean emptiness. The space between stars is not a void in the way a room emptied of furniture is a void, bare and inert and waiting. It has weight to it, in a sense. Texture, temperature gradients that shift across distances measured in light years. Some of it is cold beyond anything the solar system naturally produces. Some of it burns hotter than the surface of the sun. The same galaxy holds both these things at the same moment, separated not by walls, but simply by distance, each region going about its own slow business, in the dark between the stars. This material between the stars has a name. Astronomers call it the interstellar medium, and the name is simple enough, the medium through which interstellar space is filled, but the thing itself is more layered than the name suggests. Gas and dust and magnetic fields and high-energy particles all woven through one another in proportions that shift from cloud to cloud, from the dense cold cores of nebula to the thin hot plasma threading through the wider galactic disk. It is not uniform. It pools and thins. It clumps into dark structures that blot out the stars behind them. It disperses into regions so dilute that the word vacuum seems almost generous for the scale of emptiness found there. And through all of it, invisible radio signals travel at the speed of light, carrying information about the hydrogen that produced them, crossing thousands of light years of dust-clouded space to arrive at radio telescopes on Earth and be decoded into maps of things that cannot be seen any other way. The hydrogen itself is the dominant ingredient. Roughly 90% of the atoms in the interstellar medium are hydrogen, and most of the rest is helium, with traces of carbon, oxygen, nitrogen, and heavier elements scattered among them. These heavier elements were forged inside earlier generations of stars and distributed into space when those stars ended, seeded into the medium to drift and accumulate, and eventually find their way into clouds dense enough to collapse into new stars and the planets that form around them. The medium is not static raw material waiting passively for something to happen to it. It is actively cycling. Stars form from it, live inside it, shed material back into it, and sometimes end in explosions, energetic enough to carve enormous cavities through it and drive shock waves outward at speeds that compress surrounding gas, and in so doing, sometimes trigger new star formation. The interstellar medium is less a background and more a slow, ongoing process. The density of this material varies enormously depending on where in the galaxy the measurement is taken. Inside the densest molecular clouds, there can be as many as 1 million atoms or molecules in a single cubic centimeter. That sounds substantial until it is placed alongside something familiar. A cubic centimeter of air at sea level on Earth contains roughly 27 quintillion molecules, a number so many orders of magnitude larger that the densest interstellar cloud still counts as an extraordinary vacuum by any laboratory standard. Out in the hot diffuse regions between clouds, the numbers fall further, sometimes to fewer than 1 atom per cubic centimeter, a density that no vacuum chamber built on Earth has ever matched. The interstellar medium is full relative to intergalactic space, and nearly incomprehensibly empty relative to anything a person could hold in their hands. The dust is a smaller fraction of the medium's mass than the gas, but its effects on what astronomers can observe are considerable. Interstellar dust grains are tiny, typically between 1/10 of a micrometer and a full micrometer across, which places them somewhere near the scale of large virus particles. They are composed of silicates and carbon compounds, and in the colder regions closer to cloud cores, coatings of ice. They form on the surfaces of cool giant stars and are expelled outward by radiation pressure and stellar winds into the wider medium, where they drift and accumulate, and sometimes grow by accreting more material from the surrounding gas. Where they concentrate into clouds, they block starlight so thoroughly that the regions behind them become invisible to optical telescopes, not dimmed, but extinguished, the background stars simply absent from view, where a dense enough curtain of dust stands in the way. The Horsehead Nebula sits in the constellation Orion, rising from a larger cloud of gas and dust against a glowing background of ionized hydrogen that shines in deep red. The shape that gives it its name is a pillar of cold, dense dust, its silhouette so opaque to visible light that the stars behind it are stopped completely, present, certainly, their light traveling outward in all directions, but unable to pass through the dust column and reach any observer on the other side. The pillar itself is not smooth or solid in the way the photographs sometimes suggest. It is turbulent at its edges, eroded by radiation from nearby hot stars, its surface slowly being worn away, even as its core remains dark. The Horsehead is a temporary structure by astronomical standards, though temporary in this context means many millions of years. It will eventually dissipate. The stars behind it will become visible again, but for now the dust holds, and the stars it hides stay hidden, and the boundary between the dark pillar and the glowing background is one of the sharpest visual contrasts in the night sky. The coal sack is another such dark cloud, visible to the naked eye in the southern sky as an absence, a region near the Southern Cross, where far fewer stars are visible than in the surrounding fields, not because stars are genuinely absent there, but because a dense cloud of dust about 600 light-years away absorbs and scatters the light of the stars behind it, before that light can reach Earth. Indigenous Australian astronomers recognized it for thousands of years, incorporating it into sky maps and stories not as a blank space, but as a positive feature, a dark shape given its own identity alongside the bright constellations. The cloud is there. The stars behind it are there. only the light is interrupted. Dust does not only block, in some circumstances, it scatters and reflects. Blue light scatters more readily than red, which means that hot blue stars embedded in or near dust clouds can illuminate those clouds in blue, producing what astronomers call reflection nebulae, clouds that glow not because they are hot enough to emit their own light, but because they are scattering the light of nearby stars back toward observers. The Pleiades, the star cluster visible in winter skies across the northern hemisphere, fusion to a patch of interstellar dust, and the fine blue wisps visible in long exposure photographs of the cluster are the light of those stars reflected from dust particles too small to see individually, but present in sufficient numbers to catch and redirect starlight from across the nearby interstellar medium. Cold is a relative term anywhere in the universe, but in the cores of molecular clouds, it takes on a quality that has few parallels. A molecular cloud core can reach temperatures as low as 10 Kelvin, 10 degrees above absolute zero, the theoretical minimum where molecular motion ceases entirely. For context, the average temperature of the surface of Mars is around 210 Kelvin. The coldest naturally occurring temperatures measured on Earth reach perhaps 220 Kelvin in the upper atmosphere. 10 Kelvin is far below these. It is far below the temperature of the surface of Pluto. It is a cold so thorough that chemistry, which depends on atoms and molecules having enough energy to move and collide and react, slows to a pace that makes the word slow feel inadequate. Reactions that would proceed in seconds in a warm laboratory can take millions of years in a cloud core at 10 Kelvin. And yet they proceed. Complex carbon molecules, some of them with structures that would be at home in an organic chemistry textbook, form on the surfaces of dust grains in these cold, dark places, building up slowly in the dark. Astronomers have detected more than 200 distinct molecular species in interstellar clouds, some of them simple, like water and carbon monoxide, others more complex, methanol, formaldehyde, ethanol, formic acid, glycolaldehyde, which is a simple sugar. The chemistry of cold cloud cores is not the chemistry of a warm and active environment. It is slow, dark, low-energy chemistry conducted on the surfaces of dust grains and in the thin gas between them over timescales that stretch across millions of years. The molecules that accumulate there are not biologically significant in themselves. They are precursors, raw ingredients, components that might eventually find their way into the planetary systems that form when clouds like these eventually collapse. Whether they do, and what role interstellar chemistry plays in the eventual emergence of the chemistry of life, is a question still being examined. The collapse itself is worth dwelling on. A molecular cloud core at 10 Kelvin is, among other things, a slow accumulation of exactly the material that new stars are made from. Gravity works on it continuously. If the cloud is dense enough and cool enough and large enough, there will come a point where the gravitational energy pulling its mass inward exceeds the thermal and magnetic pressure pushing outward, and the cloud will begin to contract. The contraction proceeds slowly, at first, then faster, the center growing denser and hotter as gravitational energy converts to heat, until a protostar forms at the core, an object not yet hot enough to sustain nuclear fusion, but already glowing from the energy of its own collapse. Around it, the remaining material of the cloud settles into a rotating disk, and within that disk, over millions of years, dust grains collide and stick and gradually build up into larger and larger bodies until planets form. The cold, quiet, 10 Kelvin cloud does not stay that way. It is an earlier stage of something warmer and more active, and the dark dust chemistry that proceeded there in the meantime leaves traces in the composition of the bodies that eventually form. Within the Milky Way, the average distance between one star and its nearest neighbor is roughly 4 to 5 light years. That number carries more weight when paired with something physical. The nearest known star to the Sun is Proxima Centauri, a small red dwarf about 243 light years from Earth. This is the shortest stellar commute available from here. Light covers it in a little over 4 years, traveling at 300,000 kilometers per second. Human spacecraft travel considerably slower. The Helios 2 probe, launched in 1976 as a joint project between NASA and West Germany to study the solar wind, achieved the highest speed ever recorded for a human-made object by swinging close to the Sun and allowing solar gravity to accelerate it outward. At its maximum velocity, Helios 2 reached approximately 252,000 kilometers per hour. That is a genuinely high speed by any human scale. The distance between the Earth and the Moon is roughly 384,000 kilometers, and at 252,000 kilometers per hour, Helios 2 could cross that distance in about 90 minutes. Across the solar system, at those speeds, journeys measured in years become manageable. Mars, at its closest approach, could be reached in a matter of months, the outer planets in decades. These are long journeys by human reckoning, but they are finite in a way that feels comprehensible. The scale shifts when the destination is a neighboring star. At 252,000 kilometers per hour, the fastest any human-made object has ever traveled, the journey to Proxima Centauri would require approximately 17,000 years. Not 17 years, not 1700, 17,000, which is roughly the distance in time from today back to the end of the last ice age, when glaciers were still retreating from northern Europe and the first permanent human settlements were being established in the Middle East. The Helios 2 probe is not heading toward Proxima Centauri. It is traveling in a different direction, and even if it were pointed correctly, it would not arrive for longer than human civilization has existed. This is the nature of the nearest stellar distance, the minimum gap, the most favorable case. The average distance between stars in the galaxy is larger still. Most stars are not 4 light years from their neighbors. 4 light years is already a small number by galactic standards. What fills those 4 light years between the Sun and Proxima Centauri is not nothing. The interstellar medium extends throughout the gap. The particular region around the solar system sits within a structure called the local bubble, a large cavity in the interstellar medium roughly 1,000 light years across, carved out by supernova explosions over the past 10 to 20 million years. The interior of the local bubble is filled with hot, thin plasma at temperatures around 1,000,000 Kelvin, the interstellar equivalent of a vast, very diffuse, very hot region where the density of the medium is lower than in the surrounding galactic disk. The solar wind from the Sun pushes outward into this material and eventually meets it at a boundary called the heliopause, roughly 100 to 150 astronomical units from the Sun, which is where the Voyager probes entered interstellar space proper after their decades of travel. Beyond the heliopause, the material is no longer solar in origin. It belongs to the interstellar medium, the thin, hot plasma of the local bubble mixed with trace amounts of neutral gas and cosmic dust drifting slowly in the galactic plane. It is not a dramatic transition. The Voyager probes did not cross some visible boundary into a suddenly different kind of space. The measurements changed, the charged particle environment changed, the direction of the magnetic field changed. The spacecraft were the same, the instruments were the same. Only the context shifted from solar space to interstellar space, and the shift happened gradually over a region of space too large to perceive except through instruments. Temperature is one of the most striking things about the interstellar medium once its range becomes clear. Molecular cloud cores at 10 Kelvin are not the entire picture. The medium also contains regions of ionized hydrogen called HI regions, after the spectroscopic notation for ionized hydrogen, where hot young stars have poured enough ultraviolet radiation into the surrounding gas to strip electrons from hydrogen atoms entirely, leaving a plasma that glows in the red and pink tones familiar from photographs of nebulas, like the Orion Nebula or the Carina Nebula. These HI regions have temperatures around 8,000 to 10,000 Kelvin. Warmer still are the regions heated by supernova shock waves, vast expanding shells of gas accelerated to thousands of kilometers per second, heating material to temperatures in excess of 1,000,000 Kelvin wherever the shock wave passes. The local bubble is one such region, the product of multiple supernovae over millions of years, a cold molecular cloud at 10 Kelvin, and a hot supernova remnant at 1,000,000 Kelvin can occupy different regions of the same galaxy at the same moment. They are not far from one another on a galactic scale. The temperature difference between them is a factor of 100,000. Both are features of the same interstellar medium, different phases of the same gas, coexisting in rough pressure equilibrium across the galaxy. The cold phases are denser and occupy smaller volumes. The hot phases are thinner and fill larger regions. They are not isolated from one another. Gas flows between phases over time, cooled by radiation and compressed into clouds, then heated again by radiation and shock waves, and dispersed. The medium breathes, in a slow sense, cycling through temperatures and densities on timescales of millions of years. Radio astronomy opened a part of the interstellar medium that optical telescopes could not reach. Dust had blocked the view into large portions of the galactic disk, making entire spiral arms invisible to any telescope working in visible light. But in 1951, three groups working independently, Harold Ewan and Edward Purcell at Harvard, Alex Muller and Jan Oort in the Netherlands, and Frank Kerr and Joe Posse in Australia, detected for the first time the characteristic radio emission of neutral atomic hydrogen at a wavelength of 21 centimeters. The physics behind this signal is precise. Neutral hydrogen atoms have two possible configurations, depending on whether the electron and proton spins are aligned or anti-aligned, and when an atom transitions spontaneously from the higher energy aligned state to the lower energy anti-aligned state, it releases a photon at exactly 21 centimeters wavelength. This transition happens rarely for any individual atom, on average about once every 11 million years, but neutral hydrogen is so abundant throughout the galaxy that even this rare emission, summed across billions upon billions of atoms, produces a detectable signal. The 21 centimeter line travels through dust unimpeded. It does not scatter or absorb in the same way visible light does. A radio telescope receiving this signal from deep in the galactic plane is reaching through thousands of light years of dust that would be completely opaque to optical light. Astronomers can use it to map the distribution of neutral hydrogen across the disk of the galaxy, including the spiral arms that run behind dense dust lanes. And what those maps revealed was a hydrogen disk that extends well beyond the visible edge of the galaxy, a disk of gas broader and flatter than the disk of stars and star-forming regions that defines the visible Milky Way. The galaxy's gas reservoir is larger than its stellar disk. The interstellar medium does not end where the stars thin out. A radio telescope aimed at a particular part of the sky and tuned to 21 centimeters receives essentially a line of sight inventory of neutral hydrogen. Different clouds along the line of sight move at slightly different velocities relative to Earth, some rotating with the galaxy at slightly higher speeds because they are closer to the galactic center, others more slowly because they are farther out. And this velocity difference shifts the received wavelength slightly through the Doppler effect, allowing astronomers to distinguish the signals from different clouds at different distances and build a three-dimensional map of hydrogen distribution from what is, at its origin, a two-dimensional image of the sky. The technique is laborious. Each position on the sky must be observed carefully, each spectral line analyzed for multiple velocity components, but the maps that result show the spiral structure of the Milky Way in more detail and more depth than optical observations alone could ever provide. What those maps show, among other things, is that neutral hydrogen clouds are not evenly distributed. They cluster along spiral arms, concentrate in regions of active star formation, thin out in the interarm regions. There are dense filaments of hydrogen that appear to trace the same large-scale structure that runs through the stellar distribution. There are high-velocity hydrogen clouds moving at speeds inconsistent with simple galactic rotation, thought to be material falling onto the galactic disk from outside, gas raining down from the halo of the galaxy, resupplying the disk with fresh hydrogen from outside the plane. The medium is not just cycling within the disk, it is also accreting material from the wider galactic halo, adding new hydrogen to the reservoir that will eventually form stars. The gap between the Sun and Proxima Centauri is approximately 243 light-years, and inside that gap, the interstellar medium is present, thin and hot, the plasma of the local bubble threading through it at a density far too low to interact with anything in any perceptible way. A spacecraft crossing it would feel nothing. The plasma would pass through the spacecraft, and the craft would pass through it without any measurable resistance. The interaction would be essentially zero. What the medium provides in that stretch of space is not resistance or texture in any direct physical sense, but a context, a setting that places the solar system and its nearest neighbor within a shared environment, the same galactic region, the same local bubble, the same slow cycle of heating and cooling and eventual star formation that governs the interstellar medium across the entire disk. Somewhere in the Milky Way right now, a molecular cloud is approaching the conditions for collapse. Its core is cold, close to 10 Kelvin, its outer layers still warming slightly under the faint radiation of distant stars. Turbulent motions are damping out inside it as the gas radiates away energy and cools. Magnetic fields thread through it, slowing the collapse in the plane perpendicular to the field lines, channeling the infalling gas along the field direction instead. Dust grains at the core are coated with layers of ice, water ice, carbon monoxide ice, on which complex molecules have been slowly assembling for millions of years. The cloud does not know it is about to become a star. Nothing here is purposeful in that way. The process is just physics, gravity pulling inward, pressure pushing out, and at the moment when gravity wins, the slow collapse begins that will eventually light a new sun somewhere in the galaxy. That process, from cold dark cloud to new star, takes on the order of 1 to 10 million years, depending on the mass of the star forming and the initial conditions of the cloud. For the most massive stars, it goes faster. For the smallest red dwarfs, it goes slower. The disk of material that forms around the protostar can persist for several million years, within which time the grains of dust begin to stick together and grow from micrometers to millimeters to centimeters to larger aggregates until eventually the process of planet formation begins in earnest. The chemistry that was proceeding on those dust grains at 10 Kelvin, the complex carbon molecules building up over millions of years in the cold and dark, will end up incorporated into the material of the forming system. Some of it will fall into the star and be destroyed. Some of it will be incorporated into planetesimals and eventually into planets. Some of it will remain in the outer reaches of the system, in comets and icy bodies, where it might persist for billions of years without further alteration. The distances between stars make all of this private. One forming system cannot communicate with another on any timescale that is short relative to the formation process itself. Two protostellar systems 10 light years apart are effectively isolated from one another while they form. Light from each reaches the other in 10 years, but the formation process takes millions. Whatever happens in one cloud happens without reference to what is happening in the next. The interstellar medium connects them. In a sense, both are condensations of the same wider gas reservoir, seeded with the same heavy elements from previous stellar generations, but the individual events of collapse and accretion and planet formation are separate, private, occurring across a silence that is not hostile, simply immense. The medium itself communicates over these distances in one important way. Radiation, ultraviolet light from hot young massive stars, X-rays from neutron stars, and accreting black holes, energetic particles from supernovae and stellar winds crosses the interstellar medium and alters the chemistry and temperature and ionization state of gas clouds far from the source. A supernova can send a shock wave through the interstellar medium that reaches a neighboring molecular cloud thousands of light years away, years to millennia after the explosion itself, compressing the cloud and potentially triggering the collapse of regions that would not otherwise have formed stars on their own. Whether the sun formed in part because of a nearby supernova's compression of its parent cloud is a question that has been explored in the astronomical literature, with some evidence for a supernova enrichment event in the early solar system drawn from specific isotope ratios in meteorites. The interstellar medium is not passive between these events. It carries the signals. Among the most persistent facts about the space between stars is simply how cold it can be and how long it stays that way. A molecular cloud core that has been sitting at 10 Kelvin for 10 million years has been sitting at 10 Kelvin, undisturbed, for longer than hominids have existed on Earth. It has been cold and dark for longer than the continents have been in their current positions, longer than the Atlantic Ocean has existed in its present form. The chemistry proceeding on its dust grains has been proceeding slowly, in the dark, since before whatever was forming on Earth, at the time those dust grains first acquired their ice coatings. There is a persistence to the cold regions of the interstellar medium that sits outside the usual scales human experience provides for estimating how long things take. And yet the cold does not last forever. The collapse that eventually ends it is, in a sense, the cold cloud's completion, the conclusion of a slow accumulation that began with gas dispersed by earlier stellar generations and ends with new stars, and around them the possibility of solid bodies made partly from the chemistry that proceeded in the dark and the cold for millions of years before the collapse. The interstellar medium cycles. The cold, dense clouds are one phase of a long cycle that begins in the diffuse gas of the galactic disk and passes through star formation and stellar evolution and eventual return of material to the medium by stellar winds and supernovae and planetary nebulae, nothing is wasted, nothing sits in the cold indefinitely. Given enough time, the medium reorganizes itself, and the cold, dark chemistry in the heart of a molecular cloud becomes the raw material of something new. A molecular cloud core at 10 Kelvin, colder than any temperature naturally found in the solar system, darker than any region illuminated by the sun's light, denser than the thin hot plasma of the local bubble by many orders of magnitude, sits quietly in the Milky Way right now, invisible to optical telescopes, its structure mapped only by radio and infrared observations, its dust grains coated with ice and organic molecules built up over millions of years of slow, cold chemistry. Gravity is working on it. The same physics that shaped the solar system is working on it. It does not know this. The process is not aware of itself. But the accumulation continues, and the slow gathering of material toward the moment of collapse continues. And somewhere in the cold and quiet of the space between stars, something is in the early stages of becoming something else, not urgently, not on any time scale that measures itself in human terms, but steadily, as these things have always proceeded. The interstellar medium going quietly about the long business of turning darkness and cold and dust into light. In the summer of 1950, at Los Alamos National Laboratory in New Mexico, a group of physicists sat down to lunch together in the way that physicists often do, talking about something else entirely. The morning's conversation had apparently been about a cartoon in the New Yorker depicting flying saucers, and about reports of objects that had gone missing across New York City. And the men at the table had been making light of the whole thing in the way that people do when a topic is amusing without being serious. Enrico Fermi was among them. He was, by any measure of the time, one of the most accomplished physicists alive, the architect of the first artificial nuclear reactor, a man whose instincts about physical problems had an almost uncomfortable reliability. And at some point during that lunch, after the conversation had moved on to other things, Fermi put down whatever he was holding and asked, out of a clear sky, 4 words, "But where is everybody?" His colleagues laughed. The question was funny, partly because it was so sudden, and partly because it was on its surface so simple. A child's question. The kind of thing someone asks when they walk into a room they expected to find full of people. Fermi's question, though, was not about the room. It was about the galaxy, and about the fact that the galaxy is very old, and that any civilization that had arisen anywhere within it, several 100 million years ago, would have had enough time, even traveling at modest fractions of the speed of light, to spread across every habitable corner of it many times over. There are hundreds of billions of stars in the Milky Way. The galaxy has been forming stars for roughly 10 billion years. The conditions for planetary formation have been understood to exist around a substantial portion of those stars, and yet the cafeteria was quiet on that particular point. No confirmed signal, no artifact, no visitor. The question hung there above the lunch tray, patient and unanswered. What made the question so durable was not that it implied something frightening. It was simply that the arithmetic, however approximate, seemed to make absence harder to explain than presence. The mathematician Edward Teller was at that table. So was Herbert York and Emil Konopinski. None of them had a satisfying answer. Fermi, who had a habit of estimating things from first principles with nothing more than a piece of paper and a reasonable set of assumptions, apparently made a quick calculation of the probability of extraterrestrial life on his own and found the resulting figure surprisingly high. which made the silence around the table and the silence beyond it all the more particular. The silence, it turned out, would persist. 11 years after that lunch, on a November evening in 1961, a group of astronomers and scientists gathered at the National Radio Astronomy Observatory in Green Bank, West Virginia, for a meeting that would later be called the First SETI Conference, the first organized effort to think rigorously about the problem of searching for signs of extraterrestrial intelligence. There were 10 people in the room. Frank Drake, a radio astronomer who had recently conducted the first modern radio search for extraterrestrial signals using the Green Bank telescope, wrote an equation on a blackboard at the start of the meeting, not as a formula intended to produce a definitive number, but as a way of organizing the problem, of identifying which questions actually needed to be answered before the larger one could be approached. The equation Drake wrote out was a chain of factors, the rate at which stars form in the Milky Way each year, multiplied by the fraction of those stars that have planets, multiplied by the number of planets per system that might support life, multiplied by the fraction on which life actually arises, multiplied by the fraction of those where intelligence develops, multiplied by the fraction of intelligent civilizations that develop detectable technology, multiplied by the average length of time such a civilization remains detectable. Each factor in turn. The product at the end of the chain was an estimate of how many communicating civilizations might exist in the galaxy right now, at this moment, sending signals that a sufficiently sensitive instrument might detect. The first few factors in that chain are now reasonably well measured. Stars form in the Milky Way at a rate of somewhere between 1 and 3 per year. The fraction with planets has been revised sharply upward since 1961. Data from the Kepler Space Telescope and its successors suggest that most stars have planets, and that rocky planets in or near the habitable zone of their parent star are common rather than rare. The number of potentially habitable planets per system is harder to pin down, but estimates have become more grounded with each passing decade of observation. It is the later factors, the fraction of planets where life arises, the fraction where intelligence follows, the length of time a civilization remains detectable, where the estimates diverge so dramatically that different researchers using the same equation arrive at answers ranging from less than 1, meaning we are likely alone in the observable universe, to millions, meaning the galaxy is presently teeming with signals waiting to be received. That range of answers is not a sign the equation is broken. It is a sign that the equation has done exactly what Drake intended it to do. It has mapped the shape of the ignorance precisely enough to show which questions need to be answered next, and it has given the search a coherent structure in the decades since, a framework inside which a single unexpected data point, arriving from any direction, could immediately shift every estimate in the chain. The data point that came closest to doing that arrived on an August evening in 1977. A volunteer astronomer named Jerry Emmon was working at the Big Ear Radio Telescope at Ohio State University, which had been conducting a sky survey as part of a SETI program. Big Ear was not a dish in the traditional sense. It was a flat reflector and a tilted reflector, a design that allowed it to scan the sky as the Earth rotated, picking up signals from successive strips of the celestial sphere. It operated on a narrow band of radio frequencies, and its data was printed out in columns of numbers and letters on long sheets of paper. Most of those columns were unremarkable. The numbers settled into a background hiss, a thermal noise, predictable and uninformative. On August 15, 1977, Emmon was working through a printout of data from 3 days earlier. August 15th was the date he reviewed it, not the date it was recorded, and he was moving his eye down the columns in the practiced way of someone who had done this many times without finding anything. And then he found something, a sequence of characters that bore no resemblance to the background, 6EQJ5. In the notation Big Ear used, the numbers and letters represented the strength of a received signal on a scale from 0 upward, where digits covered 0 through 9, and letters continued the scale from 10 upward. The signal had risen steeply, peaked at a value corresponding to the letter U, roughly 30 times the background noise level, and then faded just as steeply back to nothing. The whole event lasted 72 seconds, which was exactly the length of time Big Ear would be expected to observe a fixed point in the sky as the Earth rotated. It was narrowband, which is significant because natural radio sources tend to emit broadly across many frequencies, while a narrowband signal is the kind of signal a transmitter would produce. The frequency was close to the 1420 MHz emission frequency of neutral hydrogen, a frequency that some researchers had theorized an intelligent civilization might choose precisely because it is the most common radio frequency in the universe, and any spacefaring civilization capable of radio astronomy would know it. Emmons circled the sequence in red pen and wrote one word in the margin: wow. The sheet of paper is kept in an archive. The word is still there, in red ink, next to the circled characters. It has become one of the more quietly extraordinary documents in the history of radio astronomy, not because of what the signal was, which is unknown, but because of what it has remained unexplained. In the years following the detection, Big Ear returned to the same region of sky on many subsequent occasions and found nothing. In 1987, Eamon himself led a dedicated effort to redetect the signal, using the same telescope and the same frequency, and found nothing. Other telescopes have searched the same coordinates. The signal has never recurred. What the investigation established was not nothing. It ruled out several natural explanations. The signal was unlikely to have been terrestrial interference of certain types, and its profile matched the expected signature of a point source rather than a diffuse one. What it could not establish was any positive identification of the source. The signal remains, in the official record, unexplained. Unexplained is different from inexplicable. There are several natural hypotheses that remain under consideration, including interstellar scintillation, the way that radio waves passing through clouds of interstellar plasma can be briefly amplified in ways that might produce a transient spike at one telescope without being detectable at another. None of these explanations has been definitively confirmed. The sequence of characters sits in its archive, circled in red, as patient as the sky that produced it. What the wow signal gave the search was not an answer, but a different kind of information. The knowledge that if a signal of that profile existed, the equipment then available could detect it. That the search was not in principle futile. That the silence of all the other printouts, with their background hiss and their unremarkable columns, was real silence and not simply the absence of the right instrument to read what was there. The silence continued. It continues now. And there is a way of sitting with that silence that does not require resolution, that allows it to simply be what it is, which is a condition of the universe that has not yet produced a particular kind of result. The galaxy is old enough that the question is genuinely open. Whether life is common or rare across the universe remains one of the few questions in science whose answer, when it comes, will be of a kind that cannot be gradually approached. It will arrive, like the wow signal itself, as a discrete and unmistakable event, or it will not arrive at all. Meanwhile, light continues to travel. The Andromeda Galaxy is visible to the naked eye from a dark site on a clear autumn night in the northern hemisphere, as a faint and slightly elongated smudge sitting above the plane of the Milky Way. It is not dramatic. Most people who find it for the first time are mildly surprised by how unimpressive it appears. A soft blur, something that might be mistaken for a patch of thin cloud. It has to be seen with averted vision, looking slightly to the side of the point where it sits, because the rod cells in the peripheral retina are more sensitive to faint light than the cone cells at the center. The technique is counterintuitive. To see something faint, look slightly away from it. What is arriving at the back of the eye when the faint smudge resolves is light that left the Andromeda galaxy approximately 537 million years ago. That is the current best measurement of its distance, 537 million light years. A light year is the distance light travels in 1 Julian year at its standard speed in a vacuum, approximately 946 trillion kilometers. Multiply that by 537 million, and the result is a distance that no unit of everyday experience can make comfortably intelligible. But the time the light has been traveling is a unit that does connect to something. 537 million years is a long time in human terms, and it is a long time in evolutionary terms, and it is a long time in geological terms. And when that smudge resolves faintly in peripheral vision on a dark autumn night, the photons arriving at the retina have been in transit since before the first stone tools were knapped on the African savanna, before Homo habilis walked, before the genus that eventually produced the person looking up had arrived at anything resembling its current form. Andromeda itself contains roughly 1 trillion stars. It is larger than the Milky Way by most estimates, and it is approaching the Milky Way at approximately 110 kilometers per second, drawn by mutual gravitational attraction across the intergalactic distance between them. In approximately 5 billion years, the two galaxies are expected to begin merging, a slow gravitational interpenetration that will take hundreds of millions of years to complete, and will rearrange both galaxies into a single different structure. When that eventual merger produces its first new wave of star formation, the universe will be nearly twice as old as it is now. The light currently leaving the Milky Way's billions of stars is, right now, crossing that same 537 million light years toward Andromeda. It will arrive in 537 million years. There is no one to receive it now, or if there is, what receives it will be something so different from anything on Earth that the word receive cannot be assumed to carry any particular meaning. The light travels regardless. It has been doing so since the galaxy began producing it. A photon departing the surface of the sun at this moment will, if nothing absorbs it along the way, eventually reach the edge of the observable universe and continue beyond it into whatever extends there, a region from which, by the physics of cosmic expansion, no information can ever return. Light does not experience this journey as a duration. A photon, moving at the speed of light, has no proper time. In the relativistic sense, no time at all passes for it between its emission and its absorption. Every photon in the universe, from this frame of reference, leaves its source and arrives at its destination instantaneously. The duration that observers measure, 537 million years, 8 billion years, belongs to the space the light crosses, not to the light itself. This is one of those facts about the physics of the universe that becomes stranger the longer it sits, not because it implies something threatening, but because it quietly decouples two things that common experience treats as inseparable: the journey and the time the journey takes. The oldest light that can be observed from Earth left its source not from a star or a galaxy, but from the universe itself, or rather, From the moment when the universe first became transparent to light, for approximately 380,000 years after the Big Bang, the universe was filled with a dense, hot plasma of particles so tightly packed that photons could not travel freely. They were scattered almost immediately, the way that sunlight is scattered inside a thick cloud, which makes the interior of the cloud opaque, even though the particles within it are not individually solid. As the universe expanded and cooled, there came a moment when the temperature dropped enough for electrons to combine with protons and form neutral hydrogen atoms, and in doing so to stop scattering light. This transition happened over a relatively short period on a cosmological scale, and the photons that had been trapped in the plasma were suddenly free to travel. They have been traveling ever since. That moment was approximately 13.8 billion years ago. The photons released then have been crossing the expanding universe for all that time, and they arrive at Earth from every direction in the sky simultaneously, not from any particular source, but from the entire surrounding sphere of that ancient plasma, the surface of last scattering, as it is called in the technical literature. By the time they arrive, they have been stretched by 13.8 billion years of cosmic expansion. What began as infrared light, warm by the standards of the plasma that emitted it, has been redshifted down into the microwave part of the spectrum. The radiation arrives at a temperature of approximately 725 Kelvin, 725 degrees above absolute zero, and it fills the entire sky uniformly in every direction at every moment. It was found by accident. In 1964, two radio engineers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey, using a large horn-shaped antenna that had originally been built to communicate with the Echo satellite. The antenna was sensitive and well characterized, and Penzias and Wilson were trying to calibrate it carefully for a program of radio astronomy observations. They found in their measurements a persistent low-level noise that they could not account for. It came from every direction equally. It did not change with the time of day or with the season. It could not be eliminated by pointing the antenna at different parts of the sky. They checked the instrument carefully. They found, inside the horn antenna, that pigeons had been nesting and had left behind what their later published paper described, with considerable understatement, as a white dielectric material. They cleaned the antenna. The noise persisted. What the noise was, Penzias and Wilson discovered through a conversation with theorists at Princeton who had been working on exactly this prediction, that a relic radiation from the early universe should exist and should be detectable at roughly this temperature and in exactly this form, uniform, isotropic, and present in every direction. The paper Penzias and Wilson published in 1965 was careful and measured. It described what they had found and acknowledged the tentative cosmological interpretation without overclaiming. The 1978 Nobel Prize in Physics was awarded to them for the discovery. The radiation they found is now called the cosmic microwave background, and it has been mapped in extraordinary detail by 3 successive satellite missions: COBE in the 1990s, WMAP in the 2000s, and Planck in the 2010, each of which revealed more of the subtle temperature variations across the sky that encode information about the earliest structures of the universe. The cosmic microwave background is not an edge. It is not a boundary of the universe. It is a limit of visibility, the furthest back in time that electromagnetic observation can reach, because before that moment the universe was opaque and photons could not travel freely. It is, in a sense, a horizon in time rather than in space, the universe before it existed and was in motion, but no light from it survives to carry a direct image of what it was doing. The photons of the cosmic microwave background are the oldest light that any instrument on Earth can detect, and they carry in their slight temperature variations the imprint of density fluctuations in the early plasma, the seeds from which all the subsequent large-scale structure of the universe grew. What this means, held lightly, is that the universe has been sending the same signal continuously for 13.8 billion years. Not from a single direction, not from a single source, but from every direction simultaneously. A uniform microwave warmth permeating all of space at all times. The leftover glow of an early state that no longer exists anywhere in the universe, but whose light has been traveling ever since. Every square meter of every surface on Earth is being reached, right now, by that radiation. It passes through walls, it passes through the atmosphere, with most of its energy intact. It passes through everything that is not specifically designed to absorb microwaves at that temperature, and most things are not. At this moment, some fraction of the faint hiss that an untuned analog television once produced between channels was the cosmic microwave background, the most ancient light in the observable universe, received by an ordinary consumer electronic device in an ordinary room. The signal arrives without urgency. It has no particular preference for arriving now rather than at any other moment. It arrives at every moment equally, has been arriving at every moment since the universe became transparent to it, and will continue arriving at every moment until the expansion of the universe has stretched its wavelength to such extreme lengths that it becomes undetectable even to instruments far more sensitive than anything currently built. That is a very long time from now. For present purposes, the universe is still transmitting. There is something particular about that fact. When held alongside Fermi's question, and alongside the 72 seconds of a radio signal that has never been explained, and alongside the 537 million year journey of the Andromeda smudge, they are all in different ways about the same thing: light and signal and time, and the specific kind of patience required to receive something that has been traveling toward you for longer than you can comfortably imagine. The cosmic microwave background asks for no response. It simply arrives in every direction at 725 Kelvin without preference for whether anyone is listening, somewhere else to something else, is a question the Fermi lunch did not resolve, and the Drake equation cannot answer with the information currently in hand, and the wow signal did not settle, and probably will not be settled on any particular night, or in any particular observation. The galaxy contains what it contains, and most of what it contains is old and slow, and in the process of doing things that will only be visible as processes from a very great distance of time. Stars are forming, right now, inside cold, dense clouds of gas and dust, where the temperature approaches 10 Kelvin, barely above absolute zero, and where the slow gravitational collapse of those clouds is accumulating material that will, over the course of millions of years, become something new. The material has been there for a long time. The collapse is quiet and gradual. There is no moment at which a future star announces its intentions. It simply becomes denser, and then denser still, until the pressure at its core is enough to ignite nuclear fusion, and then it shines. The time between the beginning of a molecular cloud's collapse and the ignition of the star at its center is measured in millions of years. The star itself, once ignited, will burn for millions or billions more, depending on its mass. The light it produces will cross whatever distance separates it from whatever else exists in the galaxy, arriving where it arrives after a delay measured by the distance divided by the speed of light. If there is anyone anywhere to receive that light, to notice it as the signature of a new star, or as the specific spectral lines that indicate a particular element in its atmosphere, or as the slight dimming that indicates a planet passing across its face, they will receive it long after it was sent. Every observation of every object in the universe is an observation of the past. The present state of the universe is, strictly speaking, unobservable. What can be seen from any point is only what light has had time to carry from other points, and the light takes time to travel. This is not a limitation that can be engineered around. It is a feature of the physics of the universe, and it is the same feature that gives the cosmic microwave background its particular character. The universe's past is genuinely visible to an observer with the right equipment, in a way that the universe's present at any distance is not. The night sky is always a map of the past. The familiar stars overhead are seen as they were years or decades ago. The distant galaxies are seen as they were millions or billions of years ago. The microwave background is seen as the universe was 8 billion years ago. Each layer of distance adds a layer of time, and the deepest observations reach the furthest back until the opacity of the early universe draws a horizon that cannot be crossed by any photon. Beyond that horizon, the universe is not absent. It is simply opaque to this particular method of looking. The matter that was present before the cosmic microwave background was emitted is the same matter that later formed the first stars and galaxies, and much of it is present in some form today, in the stars and gas and dust of galaxies, in the intergalactic medium, in the large-scale structure of filaments and voids. The earliest state of the universe is not gone. It has continued, as all physical systems continue, evolving through successive states according to the laws that govern it, and the current state of the universe is what that evolution has produced so far. The universe at 13.8 billion years old is a middle-aged universe, by most estimates. The era of star formation has been declining for several billion years, and will continue to decline, and the long future of the cosmos, the era in which the last stars exhaust their fuel and cool into dark remnants, stretches ahead for a time measured in numbers so large they become difficult to hold, even as abstractions. But that future is genuinely there, built into the same physics that produced the past, continuous with the universe that the cosmic microwave background photographs in microwave light. For now, though, the background is 725 Kelvin. It fills the sky in every direction. It has been filling the sky for longer than the Earth has existed. On this particular night, as on every other night, it arrives at the surfaces of things, at telescope mirrors and radio antennae, and the roofs of buildings, and the surfaces of oceans, and the faces of whatever happens to be facing upward in the dark, without interruption, without preference, without urgency, as it has been arriving since the universe first cleared and the photons were set free to travel. There is a quality to that continuity that is quieter than any of the other large facts about the universe. The size of the observable universe is large enough to resist imagination. The distance to the nearest star is large enough that all of human history would fit many times into the time it would take to cross it at any speed humans have achieved. The Fermi question is open enough that it cannot be answered without information that does not yet exist. But the cosmic microwave background simply arrives. It is not waiting for a response. It is not addressed to anyone in particular. It is the universe's oldest ongoing transmission, and it is happening right now, at this moment, in every direction, at 725 Kelvin, crossing the whole observable universe and arriving at every point within it simultaneously, the faintest possible warmth, too faint to feel and too cold to see, but measurable, present, persistent, still arriving after 13.